Well, hello everybody. Today is a very exciting session because we're actually going to start the area of integral calculus, which is otherwise affectionately or sometimes not so affectionately known as anti-differentiation. So let's make a start. This is a pretty lightweight session, so it won't be that hard to follow, but it sets the scene for what this stuff's all about. Okay, so we're doing approximations to areas under curves, and we're leading to what's called the definite integral. Okay, definite integral. And the geometrical significance of anti-differentiation, in case you haven't already been told this, is all about areas under curves. That's what we're kind of leading to here. So we're leading you in that direction today. Excuse me. So we're going to do three things today. We're going to do left-hand estimates to areas under curves, right-hand estimates to areas under curves, and we're going to introduce you to the idea of a definite integral, which is the exact area under a curve between two, a left-hand and a right-hand value of x in between those. Right, what have we got here? Well, we've got a graph, and we've got a graph of f of x is 9 minus 0.1x squared. And this is how we're going to do it. We're going to basically guesstimate the area under this graph by using the left. We're sectioning it off into little rectangles, and between the areas of x is 2 and 5 with 0.5 intervals of x. So that makes 6 rectangles all told. R1, 2, 3, 4, 5 and 6 as they're labelled. And we're going to use the y values, the heights of these rectangles, which is the y value of the function, at the left hand side of each rectangle, the left-hand value of x for each rectangle. Okay, so that means for R1 we would use the value of y when x is 2, and we would multiply that by 0.5, which is the width, and that would give us that first area of the rectangle. Okay, we're using y is 2. We do the same thing for the second rectangle, but this time we would use the value of x is 2.5, and then multiplying that by 0.5 we'd get the second area, and so on and so on. You get the idea? Okay, let's do the third one. We would be using the value of x is 3 as the left-hand end of that rectangle. Therefore the y value, we'd plug that in to the formula 9 minus 0.1 times 3 squared, and we get our y value multiplied by the width, and we get the area. You see? And you do the same thing with the fourth one, and you do the same thing with the fifth one. It's tedious, isn't it? Huh? It's tedious, but hey, it gives you an estimate of the area under the curve. And that's that one. And the last one, we do the same thing using the left-hand side of the rectangle to get our y value, and we get the area. Okay? Now, that's the procedure. That's the procedure. Okay? Now, delta x in this case was 0.5, little change in x, and that's what I call the width of the rectangle is a small change in x. And by the way, the smaller the better, because as we'll go into in a minute, there's our limits. I'm calling them a and b. I'm trying to generalize this now. So therefore the delta x, or the width, was 5 minus 2 divided by 6 rectangles. That would be 3 divided by 6, which would be 0.5, which we already knew. Now, in general terms, that's b minus a all divided by n. Okay, that's the width. So the area basically is equal to y at the value of x is 2 times the width, plus y at the value of 2.5 times the width, plus da-da-da-da-da-da-da-da, and the last one is y at 4.5 times the width delta x. Okay. Now, that's individually adding them all up, but of course, if you think about that, if you factorise that little expression that I've just come up with taking out delta x as a common factor, if you like, you could also get it by just basically adding up all the left-hand side y values and multiplying them by delta x. It's the same thing, okay? It's the same thing. Yeah, multiply them by, in general terms, b minus a over n. So that is really the formula, if you like, if you want to use a formula, for adding up these rectangles and their areas. If you like, you can just work out each individual area and add them up, or you can use that formula, which is a little bit more fancy. But it's pretty intuitive, isn't it? Now, in this case, we've overestimated the area under that curve, because you can see all those little bits of rectangles sticking up above the curve. Well, that's not actually area under the curve, those bits, are they? They're overestimates. As you'll see, watch me colour them in. Ooh, isn't that fancy? That is the overestimated area, okay? Well, that's a bit of a problem, isn't it? Well, let's think about how we might correct that a bit later on. Now, just as in the previous screen we had an overestimate for a curve which was curving, going flatter or curving downwards as x progressed, this one's curving upwards as x progressed, and in this case we get an underestimate. My goodness, voila. Now, have a look. How can we reduce this inaccuracy? Well, I've just showed you. We can reduce the width of our rectangles, and you'll see in that case that we get smaller values of the space that we haven't actually counted in that case. This is an underestimate we're looking at now, you see? But the downside of that is, of course, the more rectangles we create, the more work we're creating, because the more calculations we've got to do, you see? That's the problem. Life is full of compromise, isn't it? So less width means more accuracy, but more calculations. So that is a bit annoying. However, fear not, we have a marvellous, marvellous way of overcoming this coming up. But you have to know how to do this stuff, because you're going to get asked in the exam, okay? Alright, now we're going to do the right-hand estimate. Well, the right-hand estimate uses exactly the same procedure, except, as you might have already guessed, we don't use the left-hand side of the rectangle. We basically use the right-hand side of the rectangle touching the curve instead of the left-hand side touching the curve. Okay? So if you have a look at that R1, 2, 3, 4 and 5 and 6 this time, you'll see that the right-hand edge of the rectangle is drawn to coincide with the curve, whereas in the previous screens the left-hand side was used to coincide with the curve. Now, in this case, you can see it's what kind of an estimate is it? Is it under or over? Of course it is. It's under. Now, let's go through the whole tedious procedure. We use the right-hand side of that one. So that's the first rectangle. We use the value of y when x is not 2 this time, but 2.5. Okay, last time with the left-hand estimate, we started with the left-hand side of the rectangle, which was when x was 2. This time we're doing it when x is 2.5. Okay, and then we just multiply that by the width and we get the area of that one, and that's when x is 2.5. We go through the whole tedious procedure with the whole thing. That's the second one, and that's when x is 3. There's the third one, right-hand edge, right-hand height, and multiply by the width, we get that area, and that's when x is 3.5. And when x is 4, excuse me, got a frog in my throat, and that's the fifth one, and that's yes, there we go, and that's when x is 4.5, and then the last one when x is 5. Okay, yeah, that's it. Now, in this case, of course, the area is the same calculation as before, except we're using the right-hand side y values, okay, when for the values when x is at the right-hand value of the right-hand side of the rectangle, and we multiply that by the width, okay? So that's the sum of all the right-hand side y's times b minus a over n, if that's b and that's a and that's n, in which case in this case n is 6. You get the deal, don't you? Yeah? And in this case, of course, as I just said earlier, this is an underestimate. Watch. Ooh, that's fancy. Okay? It's an underestimate for this curve. Just as for this shaped curve with the left-hand estimate, it was an overestimate because we had the left-hand part of the rectangle coinciding with the curve, and therefore the right-hand side was a little bit over. You know what I mean. Now, in this case, we're going to do the curving upwards curve for the right-hand estimate, and you can see that in this case it's an overestimate, the reverse of what the left-hand procedure was. Okay, it was an underestimate. How can we improve the accuracy? Again, we can reduce the width of our rectangles, and we'll get less space counted that we didn't want counted in this instance. And less width means more accuracy, but of course you get more calculations, and that's tedious. Alright, that's left-hand and right-hand estimate. Now you can do that. That's really easy stuff. Now this is what's called the definite integral. We're introducing you to the definite integral. Now, I hinted to you before, if we reduce the size of our rectangle, the width of our rectangles, that is, if we basically keep going with that concept, and we were able to go so small with the width of those rectangles, that's the delta x, so very, very small that we were infinitely small, and we would have infinitely many rectangles, but the result would be completely accurate. It's if we were able to do that, okay? It's just a concept. You can't have infinitely many anything, but leading towards infinitely many rectangles, you'd have infinite accuracy, and you'd have infinitely small widths. That's the concept that we use for the exact area under the curve. So we say that, oh goodness, what's that thing? We say that the limit, well, first of all, that funny looking Greek capital sigma means the sum of in maths land. It means the sum of, and what's behind it is, the right hand side of it is yi times delta xi, means all of the y's, the heights, multiplied by their widths, that's in other words the area of all the rectangles under that curve added up, where I goes from A at the start up to B at the finish. In other words, it means y1 times delta x1 plus y2 times delta x2 plus y3 times delta x3 plus da 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 da, right up to the very end when we have the value of x at B. Right? Okay, and we're taking the limit of that whole thing as delta x approaches 0. So we get completely accurate, no wasted space, no overestimate, no underestimate, no anything, just accuracy. And that's called, yep, that's what all that is. That's called the integral, or the definite integral, okay, of, and you'll see behind that funny looking snaky symbol there, you've got y times delta x. Now that means the same thing, as you can see to the left. That means the height is the y, and the delta x is the limit. The dx is the limit of delta x as delta x approaches 0. It still represents the sum of a whole lot of little rectangles under the curve from x is A at the start till x is B at the finish. That is called a definite integral, ladies and gentlemen, and that is the fundamental basis of integral calculus, okay? Yeah, that is the exact area from A to B, and that is called Leibniz notation, after a famous German philosopher and mathematician from the 17th century, and his name was Gottfried Wilhelm Leibniz, and he lived in the 17th century. Wacky do. So, and that funny looking snaky looking thing, that symbol, which I've said is the Leibniz notation, is a lazy S standing for the sum of. The sum of, okay? That's what it means, right? Da-da-da-da! Now, as to how you actually do these definite integrals, we're not going to deal with that today, but we will just deal with some exact areas, some nice simple ones to get you used to the idea that the Leibniz notation is referring to the exact area, okay? Yeah, that S is for sum. Now, we're going to do a couple now. Right, this is very, very simple, so don't get stressed over this. This is really easy. We're going to do the area, the estimated area of these two situations. Now, you'll notice the one on the top is a left-hand estimate, because the left-hand side of the rectangle is coinciding with the curve. and that's an underestimate, pretty drastic one too, wouldn't you say? And we've got the right-hand estimate is the one which I'm just alluding to underneath, because the right-hand side of the rectangle coincides with the curve, okay, and that's an overestimate, pretty drastic too. And we're asking you to calculate the estimated area using these techniques, which is pretty pathetic, but it's just the principle of what we're doing, what to show you. Alright, now, okay, the width is 0.5, can you see that? And we're just going to multiply that width by the heights, okay? So the area would be 1, that's 1, that's the first one, okay? That's the y value, 1, when x is 1, okay? Times, or plus 27.8, that's the second one, right? Plus the second one, and we're going to multiply that by the width, okay? That's the equivalent of me basically working out those two rectangles individually. The first height times 0.5 plus the second height times 0.5 is equivalent to what I've just done there. And that comes to 35 over 8 times a half, which is 35 over 16 square units. Mr. Box, are you there? Ah, thank you, Mr. Box. And we've got to the end of that one, okay? Oh, it's pretty easy. It's not rocket science, but we need you to understand the principle of what we're doing here. Okay, now this one, again, the one underneath, the width is 0.5, and now we're going to work out the area. That would be, first of all, the first height is 27 over 8, and the second height is 8, and we're going to multiply that by the width, okay? That is the equivalent of me working them out both individually, and that gets me to that funny looking thing, which is 91 over 16 square units, Mr. Box. There you are. That's how you do it, okay? It's not terribly difficult. So that's an example of left-hand estimate and right-hand estimate, okay? This one, of course, is an underestimate, and this one, of course, is an overestimate. Very drastic. If you wanted to improve the accuracy, you would split it up into less width and more rectangles and drive yourself crazy with more calculations. Yep? Okay, alright, now, this part of the exercise is we're showing you some Leibniz notation here, and we're trying to get you to think that means the exact area, okay, under those curves. So we're going to work them out. We're not going to use any formulas today. We'll teach you that later. We can definitely work that out algebraically, analytically, but today we're just going to do it conceptually from the geometry of what the curve looks like, okay? Here's number 8. Now we've got this graph of y equals x minus 1 between 1 and 3, so I'm going to draw it. There it goes, and I'm putting in my coordinates, and I'm showing you that that's the graph, and I'm going to show you the area I'm looking for. There's the area. So how do you work out the area? Come on, it's the area of a triangle. Base times height over 2. And what's the base? The base is 2, height's 2, and it comes to 2 square units, Mr. Box. There you go. It's very easy, isn't it? But this is just starting off, guys. We've got to get the fundamentals right. Number B. Alright, so what's this? This is modulus of x minus 1. No problem, between minus 1 and 3 this time. Right, let's do it. There's my scale, and here's my graph. Woo, and my intercepts. Look at them, just going like magic. Now, what do I want? I want the area between minus 1 and 3. Ah, no problem. No problem. 2 triangles. Let's work out, calling them 1 and 2. Area 1 equals area 2 for me and you. And that's they're both equal to the base times the height over 2, and the bases and the heights are the same as in the example above. So that gets me 2 square units each. So both of them combined would be 4 square units. And Mr. Box, there we go. Not too difficult, eh? Now, let's do the third one. I think we're going over the screen for that because I'm running out of room. Yeah, number C. Now, what's that? That's the area under the curve, x plus 1, between 1 and 2. Okay, here we go. There's my graph. Now, there's my intercepts. Oh, gee, look at that. There it is. And we're doing between 1 and 2, are we? Yeah, there's my intercepts. Like a good little boy, I've got to put all my endpoints and intercepts in, don't I? Yes. And there it is. There it is between 1 and 2 for me and you. That looks like a trapezium to me. And it is. Now, okay, area, that's 3 on the right hand side height, 2 on the left hand side height. Area trapezium is the average height times the average length of the parallel sides times the height, or the perpendicular bit. So what's that? That looks to me like 5 over 2 for me and you, and that's it. There's your answer. Now that gets me, that's the end of today's session. So look, it was pretty good, wasn't it? Yeah, thumbs up to you and to me. So it was easy as, but that's the fundamental, the fundamentals of what integral calculus is all about. Later on we're going to show you how to analytically work out the those same areas without drawing geometry type diagrams, okay? And you'll see it's really, really easy. Okay, thank you so much for listening to me today, as I've rambled on as usual, and we'll see you next time. Okay, bye-bye.